Okay, good morning to everybody. I was asked with Paco to give a short overview of the theoretical aspects of what is there to be done, and we decided it is very difficult to do a joint talk. Then we could split that half and so on. Then we decided, although we have prepared the slides together, we decided I'll speak mostly, and then in the end, Paco will round up and make a summary, and we'll talk also about Gaspar. Okay, then starting with the slide of Gaspar. He was not a theoretician, but the Portuguese theoretical particle physics community owes him a lot. He was very important in Portugal joining CERN. For many years, he was the voice of the Portuguese high energy physics community at CERN, and he always was in charge of negotiating with the funding agencies and CERN to make the CERN fund available to all high energy groups, including the theoreticians. Then I think the stability that we got for this more than 30 years I think is very important, and we owe a lot to Gaspar. Okay. Of course, it's very difficult to make a summary what is out there. Then I chose, of course, some topics. First, I'll tell you briefly where we are and why we are still doing physics after all the standard model, the LHC, and all the experiments achievements that have shown that standard model is very good. And then we conclude. I hope that I can give you some reasons for what is behind the work we are doing. Then start by the beginning, where we are today. And of course, we have a model. It's still a model. In some years, perhaps it's a theory. While preparing this talk, I went to YouTube and listened to talks by Gross, Wilczek, many people. And of course, my talk is very modest in comparing with those talks. In fact, the Wilczek talk was not in the future, was how is physics in 100 years? Then I think that's too much for us. But I think it was Gross that said that in a few years is no more the standard model, it will be the standard theory. Well, in short, it's a local gauge field theory, and I emphasize that all these words have a very precise meaning, and the gauge group is SU3 cross SU2 cross U1, and has some content. The content is for matter, massless spin 1/2 quarks and leptons. They are in the fundamental representations of the gauge groups. 4 forces for the carriers of the interaction. We have massless spin 1 carriers in the adjoint representation, 8 gluons for SU3, and 3 + 1 gauge fields for the combination of SU2 cross U1. And then the last thing that you need to round everything together is the X field, is a spin 0, the only one in the standard model, which is needed to spontaneously break the symmetry down to what is observed in nature today, the theory of color and electromagnetism. And in the process, this gives mass to leptons and quarks, also to the W and Z, and while the photon and gluons remain massless. This is known as the Higgs mechanism, which has been recent Nobel Prize and lots of things in the press. And the other thing which has not yet been shown or proved or discovered or whatever you want to call it is that it are the self-interaction. That's a challenge for the future. It's very difficult because these are very, very low cross-section process, but should be something that should be shown to be consistent with the whole picture. Okay, not only I've shown you the content, but of course the interactions. Essentially, we have the strong interactions for which is explained by this SU3, the interactions of quarks and gluons. Then we have the weak electromagnetic interactions. They are together in a gauge group SU2 cross U1. It acts on quarks and leptons. And after the spontaneous breaking of the symmetry, the group reduces to SU3 cross U1. That corresponds to massless gluons and the photon. Then, of course, this is not complete because this is the nice part, because essentially everything is fixed by gauge symmetry. But of course, you still have other things to fix, and you have Duke interactions. Those are more free. They are not directly dictated by the gauge symmetry. And you have parameters, masses, and mixins, which are experimentally obtained, including CB violation, which is embedded in the Cabibbo combinação Mascala matrix. And in the original standard model, the neutrinos were strictly massless. So in some sense, their masses and mixins are already beyond standard model physics, although for some people this is debatable because you could include masses in a very similar way to the leptons and quarks. Then this is, of course, 2 slides for the standard model, which means that if you know what it is. If you don't know, you remain not knowing what it is. Okay, let me just give one slide of the successes and why we should be proud. Of course, I could be here all day showing results from the experiments, especially LHC, but also lab, showing how good the standard model is. And from these thousands of plots, I just chose 2. One is the differential dijet cross-section. I like this plot because it covers like 12 orders of magnitude on the cross-section, and also large amount of the PT transverse, and you see that the agreement is extraordinary. And on the right is just the plot of this cover of the X by the Atlas collaboration. Of course, those plots, they have similar plots for Atlas and CMS for all the things that could be shown. The thing I wanted to emphasize is that the agreement with the standard model is not something which you can get very easily. It's something that you have really to work through all the machinery of quantum field theory, including renormalization and relative corrections and many things that have been done from the theoretical side to match what experimentalists do. And from the side of the experimentalists, that I'm sure you'll listen more in the next talk, it is fantastic that they were able to uncover very small cross-sections. Then I think that these plots and the thousands of plots that could be shown are a triumph for theory, because all these calculations show that we are in agreement with theory, with what is observed. But I also say that these experiments are absolutely fantastic, and in many ways they were able to do things that were more spectacular than they had foreseen before the LHC was constructed. And I think that both the theory and the experiment are in very good shape in these achievements. Then, having said that, it has been sometimes objected that, or said that the agreement is so perfect that perhaps we already know everything, and we should perhaps either go home or change field, because it's everything is already done. Of course, this sounds a bit like Lord Kelvin in the end of the 19th century. We don't know if we have a new quantum mechanics or relativity coming around the corner, but I think there are still some small problems, let's say, like in Kelvin's time. I think that we should not give up, because I think there are two main objections to this negative standpoint. That first we need to improve the experimental precision. Although I've said that the agreement is excellent, there are still things that we need to know with more precision. For instance, the X couplings are still measured, but the precision is still not what we would like, because, of course, if we test the X couplings better, perhaps we can get hints of things which we have not seen yet. And of course, that will be a challenge for the next phase of LHC, high luminosity, and so on. There are a few, I said it was a complete success, but there are a few results which normally we call anomalies, which are a few sigma away from the standard model. It's nothing. I mean, you know that sigmas come and go. But anyway, some effort has to be put to clarify this issue, and of course, this needs more experiments, more time, more devoted people to these things. And in the field of neutrinos, of course, the Dirac or Majorana nature of neutrinos has to be determined. This is a very important point from the conception of the theory. And of course, you need to know what is the amount of CP violation in the leptonic sector. There are, just to mention a few points. There are other points, but this is the first line of reasoning. The second line is that there are already experimental facts that the standard model does not explain, and we really need physics beyond the standard model, although we don't know yet what it looks like. What are the things that we have? I mean, I divided these things in two categories. The experimental facts, the observations, and the theoretical prejudices. For the facts, for the observations, we know that neutrinos oscillate, they have masses and mixings. We know there is out there dark matter. I mean, it's undoubtable, and we don't know how to explain it. The baryon asymmetry of the universe, why we are here today, needs CP violation and other ingredients. I mean, the standard model has all the ingredients, but it really does not do the job. Then we need more CP violation in the standard model. We don't know where it comes from yet. And of course, there is this question of the cosmic acceleration, so-called dark energy, which we have no idea what it is. Then there are things that we see, and we have no idea how to explain. For the theoretical side, of course, I just put here 4 points, but of course you could enlarge the list. Of course, I didn't have enough space to put more things. But of course, one of the nice things that theoreticians like is unification, and is there unification in these interactions? Why we have these two scales very far apart, electroweak and the Planck scale? Is there any problem with hierarchy and so on? We have flavor masses, mixing generations. We don't have a theory of flavor. Some people say that we don't need it. I mean, we just put the numbers, but the theoreticians really would like to understand as much as they can, and they are trying to make sense of all these puzzles. And for instance, one other question is why we have just one X. As we know, the number of gauge bosons is fixed by the group. The number of families, at least low energy families, was fixed at lab. But the number of X's is not fixed by the theory, then it's an experimental question. That's why we are looking at physics beyond the standard model. Then we have can put up a list of questions where the parameters originate, do the strong and electroweak forces unify, and so on, wide generations, what is the mechanism for the neutrino masses in mixings, what about the amount of CP violation, where it comes from, what is the nature of dark matter, what is the quantum theory of gravitation, does it unify with the standard model interactions, why the electroweak scale in Planck are so different, how many scalar bosons do exist. And I could also continue with this list. And the models that we have been studying in the last decades and are still pursuing, in some sense, they they try to address some of these questions. And of course, the ideal is to be able to address all the questions, but I think that none of the proposals address all the questions. But then I choose to just give you a few examples how you can go beyond the standard model. One possibility is the multi-X models. You just repeat the standard model for the X's. It attempts to answer how many X are there, if there are extra sources of CP violation, dark matter, and so on. What are the main points is that the standard model is a decoupling limit, which means that you always recover the standard model, predicts new scalars, then there's a possibility of discovering them, possibility of CP violation and lepton flavor violation. Supersymmetry has been around for many years, attempts to answer also these questions, the hierarchy problem, the unification, the interplay of matter and forces, dark matter. There are many new particles to be discovered. There is a very light X boson. This is a point I like to emphasize because supersymmetry could be already ruled out if the mass of the X would be like 200 GeV. They have good candidate for dark matter in successful unification. Just a slide just showing about the X mass in the standard model is free because you don't know the parameter lambda. In supersymmetry, at 3 level is below the mass of the Z, but because of the relative corrections and because the top is very heavy, you can lift the mass to the present, to the value of that is observed at LHC, which is could be a coincidence, but is a nice thing. Of course, the standard plot of supersymmetry is the unification. We should say, of course, this does not prove anything, but one thing in favor of this is that this was not done by design. I mean, it was not the purpose of the people that invented supersymmetry did not want to make this plot. It just came for free, which I think it's nice. What you can have else, you can have people have been studying grand unified theories, which are models with larger groups than a standard model, attempts to answer the unification of interactions, neutrino masses and mixings, seesaw mechanism, barriogenesis through leptogenesis. They address the question of dark matter. What are the main points? You have many new particles, you have successful unification. What is the drawback? You have too many possibilities. I just show you here a plot. We have studied, for instance, we have studied in this framework how many models you could construct, and the number is under 1,000, or it's around under 1,000 models, which means that it's difficult to pick one in 100,000. Then this is more a framework than a theory, at least at this point. But it's nice that you can have unification. You can this line, which is the intermediate scale. You can really put it anywhere. You always get unification. That's the content of this plot. You can in the previous attempts we have a weak couple, but you could also consider that the X is strongly coupling, is a bound state. These things have been around also for a while. You can construct this type of models and look what are the deviations and what you could see at the accelerators. Of course, this model is like all the others. Has a standard model limit, which is good, which means that you can explain what you see, and you can look for deviations. However, for this case and for all the others, the deviations for the standard model have not been observed, and you probably have seen this type of plots, which you cannot see very, very easily because I put 4 plots here. But the main thing is that these are exclusion limits for many different models. And the main point is that in this line here, you have TV. It means here it's, I think it's 1, here is more, it's 10. You see that you are already excluding on the TV scale most of these particles, which means that it's more and more difficult to get to this. I mean, you are getting away of some of the reasons to propose these models in first place, but we never know. I mean, it could be just around the corner. For instance, as we know, we stopped LAP just before the X, right? We could be just below the discovery of some of these particles. Why is this important? Because if you discover any of these particles, you have a hint where you should go, which direction you should go for physics beyond the standard model. Okay, I'm getting to the end. Then just one slide seeing where we have to address these questions. You all know this better than I, and next talk I'm sure we'll talk about these things. You could look at the energy frontier, accelerators, with very high energy. I mean, now we have the LHC, then we'll have the next phase, and then we are discussing new colliders for the future. You could look at intensity precision frontier. You could have LHCb, Bell, BES, and so on. There's a complementary between these accelerator facilities and the underground searches for neutrinos, axions, and dark matter. And the future for the field is going to be, of course, an interplay between these high energy frontier experiments with these underground experiments for either precision or for the cosmic frontier. Okay, and I think I get to the end, and I ask Paco also to come here, and you have now the floor. Okay.
Thank you very much. Just simply for closing and summarizing this theoretical view of how high energy physics is today, it's to emphasize that Gaspar was not a theorist, and he was an experimental physicist, and we will have today, let's say, a review on all his achievements. And a part of being an experimental physicist, what is outstanding is his personal social view on the community and how he helped to develop high energy physics in Portugal, especially creating with Mariano Gago a LEAP and consolidating the participation of the Portuguese community in CERN. In this sense, he always emphasized the importance of the innovation and the education of young people. At CERN, I was very near of him because the P of Portugal and the S of Spain are very near on the table of the CERN Council, and he always tried to push the programs for bringing technicians and young people to CERN. Especially, these pictures are part of this effort or the events that result from this effort. And he opened the doors of CERN to Brazil, and here on the right, there is competition among young teachers in Brazil for going to CERN. He also helped in the efforts for peace, and he participated as an observer in the Sesame project, and always tried to bring, let's say, all the achievements in high energy physics to the Portuguese society. There are many people, or few people, that can do things well, but very few people can do things well, and many. And Gaspar and Mariano Gago were two Portuguese that did many things and very well. Nobody, when he born in Braga in 1940, could think that high energy physics was going to have a group in the University of Minho and was going to be visible. And them, I mean, there is the picture at the bottom, and they and all of us will always acknowledge his help for the community in Portugal and in Europe. Thank you.